Welcome to this module on geospatial analysis using the Python library Geopandas. In this module, we'll introduce some of the fundamentals of geospatial analysis. You'll learn how to load and manipulate spatial data, join different data sets, and create informative visualizations, including interactive maps. First, let's ensure that we have all the necessary libraries imported. These libraries provide the functionality we'll need for geospatial analysis, data manipulation, and visualization. The code cell here imports these necessary libraries. So we have Geopandas, Pandas, Matplotlib, Seaborn, and then we have things like Contextually for a base map. We also have Map Classify, Folium, and they're all tied in to creating maps. And these are considered to be dependent libraries for Geopandas. You might notice that there's some other libraries, and these are to help us handle data coming from the web. And we also have a line of code to suppress warning signs or warning notes for a cleaner output. By now, we are already familiar with pandas, so GeoPandas will feel pretty natural for us. GeoPandas extends the Pandas DataFrame concept, but it handles specifically spatial data. It achieves this by adding a special geometry column that stores spatial objects like points, lines, polygons, multi-polygons, and so on. And these help us perform certain methods and functions that are tied into GeoPandas. So we'll start by loading a GeoPandas GeoDataFrame that contains the geometric shapes of states in the United States. We use GPD, which is the alias for geopandas.readFile function, and also fsspec.open to be able to load that GeoDataFrame from a GitHub repository. This data is going to serve as our base map. Once the data is loaded, we can explore the GeoDataFrame, which is called state shapes. And using the head method, we can take a look at some of the rows and notice on the far right, we have a geometry column. And this is where the geospatial information is stored. Here, the .info method is attached to the GeoDataFrame, and you can see the details about the GeoDataFrame. Pay particular attention to the geometry column's data type, which is listed as geometry. The info method also confirms that state shapes is a GeoDataFrame with 51 entries and a geometry column that has a D type of geometry. Geopandas allows for quick plotting of geometries directly from the GeoDataFrame. This is a great way to get an initial visual check of your spatial data. The code cell that has stateshapes.plot generates a simple plot of the United States state shapes. The output shows a basic Choropleth map of the United States. Next, we'll load a standard Pandas DataFrame containing COVID-19 cumulative cases data for the United States. This data is purely tabular and does not have spatial information yet. The info method provides a concise summary of the data frame. You can see that there are many columns, primarily date columns, representing cumulative case count. Notice that there is no geometry column here, since this is a regular Pandas data frame. The date columns are currently treated as generic objects or numbers, but their names clearly indicate dates. Now, in the COVID-19 data frame, each row represents a specific location, and the columns from January 22nd onwards represent cumulative cases on that particular date. Our goal will be to connect this case data to our state shapes GeoDataFrame based on a common identifier. First, let's identify the column containing the most recent cumulative case data. This will typically be the last column in our data frame. Then we subset the data frame to only include two data columns, province state and the latest date. The subset, now called DF latest, containing only province date and the latest date column, will be aggregated where we group by the province date and sum the cases for the latest date. And then we're also going to reset the index to make province state a regular data column rather than an index. The result of the group by method will be stored in state code cases, which will then be used where there is a dot rename method chained to it to change the column, which is the most recent date column, to total cases. And you can see the result with the dot head method here. Here we're using the unique method on the GeoDataFrame as well as the data frame to examine the state values. And we can see that there are matching state values between the two data sets. And this is important for us when it comes down to joining these two data sets together. Any values that are not consistent between the two data sets will be excluded when we do our merge. Now, since we are working with two data sets where one is a GeoDataFrame and the other one is a data frame, we will be using a standard merge using Pandas merge function. Now, if we were dealing with two GeoDataFrames where each one had a geometry column, then we would be able to use Geopandas function sjoin, where we would focus on the geometry columns and be able to join the data that way. Again, in this course, we will just focus on the standard merge. Now here, we merge state shapes GeoDataFrame with state code cases Pandas DataFrame using the state names as the common key. The code cell performs a left merge on state shapes and state code cases on the state name and province state columns respectively, creating a new GeoDataFrame called merge GDF. One thing to notice here when using the merge method that there is two keyword arguments, left on and right on. And these are necessary because the GeoDataFrame and the DataFrame have column labels that are different but have the same type of values, which are states. So the left on represents the GeoDataFrame and the right on represents the DataFrame. Now, once the merge is performed, we now have two columns containing state names. So then we drop one of them and just keep one column containing state names. Now, inspecting the merge GDF GeoDataFrame, we should now be able to see the total cases column alongside the original state shapes columns, and crucially, the geometry column. Now this merge GDF is ready for visualization. Now that we have successfully merged our spatial data with our attribute data of COVID-19 cases, we can create maps to visualize the geographic distribution of cases. We'll explore both static and interactive mapping techniques. A Choropleth map is a type of thematic map in which areas are shaded or patterned in proportion to a statistical variable. It's a great way to visualize data that varies across predefined geographic regions. To create a basic choropleth, you simply specify the column you want to visualize using the column argument in the .plot method. Adding legend equals true will display a color bar. The code cell plots merge GDF using the total cases column for coloring, setting the figure size and adding a title. The output is a static choropleth map of the United States colored by total cases. This map quickly shows us the distribution of cumulative COVID-19 cases across the states, with darker shades indicating higher case counts. We can enhance our map by choosing different color maps, or CMAP, and classification schemes using Map Classify. Classification schemes divide your data into classes, assigning different colors to each class, and this helps highlight patterns. The map classify scheme quantiles is used here, where equal number of observations per class is presented. This map provides a more nuanced view of case distribution by grouping states into 5 distinct quantile-based categories. For better geographic context, we could add a web-based base map like OpenStreetMap underneath our data using Contextually. This library integrates seamlessly with GeoPandas and Matplotlib, However, Contextually expects the GeoDataFrame to have a CRS of 3857, whereas our current GeoDataFrame state shapes and thus merged GDF are both in EPSG 4269 or a CRS of 4269. The code cell reprojects merged GDF to EPSG 3857 and stores the result in a new GeoDataFrame called Merge GDF Web Mercator. It then prints the CRS of the new GeoDataFrame. Now that our GeoDataFrame is in the correct projection, we can plot it with a base map. The output is a static Choropleth map of US states colored by total states with a quantile-based color legend and a gray open street map based underneath. This map provides excellent context, showing the geographic distribution of total cases on top of a recognizable map of the United States. The Explore method allows us to quickly visualize our GeoDataFrame on an interactive map. It automatically handles the creation of a base map and adds geometric features as a layer. When using the Explore method, we can specify the column, which will be the GeoDataFrame whose values will be used to color the map features. In this case, we're using total cases. CMap is used for the color coding of the map. Tooltip allows you to indicate a list of columns whose values will appear in a tooltip when you hover over a feature. This is incredibly useful for providing immediate information. In this example, state name and total cases are listed. So when the user hovers over a state, those two pieces of information will be presented. This map is highly engaging. You can zoom in, zoom out, pan across the map, and critically, whenever you hover over any state with your mouse, a dynamic tooltip appears. This module introduced some of the fundamentals of geospatial analysis using Geopandas, covering how to understand, load, and combine spatial and tabular data. We explored visualizing spatial patterns through both static Choropleth maps with base maps and interactive maps using Geopandas Explore method, highlighting the power of libraries like Geopandas, Matplotlib, and Folium.